We're now going to move on to our next session, and this is the next session is around techniques for artificial intelligence, machine learning, and other data science related techniques. The first speaker in this session is Yonggan Fu from Rice, who will be presenting work about GANs and also work that was done at Texas A&M. So I will hand this over to Yonggan.
Okay, thank you. So hello everyone, this is Yonggan Fu from Rice ECE department, and I'm currently a PhD student directed by Professor Yingyan Lin. So today I will share our work accepted by ICML 2020. So it's AutoGAN-Distiller, searching to compress generative adversarial networks, or known as GANs. So we are the first work try to apply AutoML to compress GANs, and we are also among the first efforts to apply NAS to GANs. So here's the main contents of my presentation today. I will start from the background and motivations, and then I will give a brief introduction about our methods and also some evaluation results. So there's a growing demand to deploying GANs on results-constrained devices. For example, you may want to apply some fancy image translation tasks like Snapchat on your mobile phones. And also there's a growing need for real-time super resolution for road monitors. However, there's a large gap between the SOTA GANs and also the result-constrained edge devices. For example, most of the SOTA GANs have large memory consumption with high computation complexity and also high energy cost, while most of the edge devices have limited battery and also limited resources with small form factors. So this needs some techniques to tackle the compression of GANs. So a direct question is that could we directly apply the conventional compression techniques on classification tasks, which is well studied, directly to the GANs? A recent paper just find that if we directly apply the conventional filter pruning methods to GANs, it will lead to a failure. For example, for this task, it's a well-known horse to zebra task. So the input is a horse, and then your GANs will translate it to a zebra here. So this is the effect of the original SOTA cycle GAN here. So you can see that if you input a horse, and then the output will be a zebra. However, if we use a conventional filter pruning on the cycle GANs, the final visualization result will be a failure, right? So this mainly caused by two reasons. First, the output of GANs is an image instead of a class label. So it's very vulnerable to for the mapping between the high-dimensional structured image spaces, and also the training process of GANs are very notorious, and I think it's very known. So there's a pioneering work in GAN compression, so they achieve promising performance. For example, about 4 times compression for compressing cycle GANs. However, they still suffer from several limitations. For example, they still rely on a cycle consistency loss. So this limits their applications only to the cycle GANs. And also, they rely on a trained discriminator, but this is not always realistic in practice. For example, in some industry applications, when you finish training a GANs, then the discriminator will be discarded, so you can never access the discriminator. And also, they build on pruning only, but we all know that there are also many different compression techniques like knowledge distillation or quantization, so it still leaves a large room for more aggressive compressions. So this motivates us to propose our AutoGAN-Distiller or AGD framework. So we are the first AutoML framework dedicated to GAN compression. And also, to tackle the above limitations, we make no assumptions towards GAN structures, log forms, nor even the availability of trained discriminators. So you can see from our evaluation later that we significantly trim down the model size and complexity of GANs without degrading the performance. Then we will go to the method part. So here's an overview of our AGD framework. So we customize the 3 components in a NAS framework, that is the search space, the proxy task, and also the search algorithm to build our fancy AGD framework. So I will start from the search space. So currently, since there's a diverse preference in the network architectures for different tasks, for example, for some GAN-related tasks like style transfer, they may focus more on the consistency of the global style instead of the local details. So it may favor shallower networks. So, and also for the image enhancement tasks like super resolution, they may focus on dense predictions or pixel level predictions. So they may favor deeper networks. So it's just like the SOTA method use different search space for not for segmentation and classification. So we also instantiate different supernets for per applications. So you can see that we mainly demo our method on two tasks, including the image translation and the super resolution. So we use a sequential supernet for the image translation task because it's hardware friendly instead of compared with the previous complex supernet in darts or other networks. And for super resolution tasks, we're motivated by the recent SOTA work called ESR-GAN. We use these residual in residual blocks to build our supernet because it can avoid the gradient vanishing problem in super resolution training. And also to aggressively push forward the compression frontier of our search method, we search for both the operator and width for each block. You can see that here's the search space for our operators. It's just like follow the SOTA networks. And also, we propose a novel width search method. So we build a super kernel, and and each block will search for the best expansion ratio. That is a subset of channels from these super kernels with some predefined expansion ratios here. And then for the proxy task, since the training process of GANs are notorious, so to stabilize the searching process, we will use a distillation loss between a pre-trained SOTA GAN network, GAN generator to at our loss or our proxy task. So you can see that here's the proxy task or loss forms, or known as objective functions of our search goal. So you can see that the G0 here is a SOTA pre-trained generator, and the G here is our supernet. So we will use the distillation loss between the two networks as our objective function. And also we explicitly introduce a computational aware loss, and in our work, it's floating point operations, to make our search GANs to be more efficient. And also the alpha and gamma here are the architectural parameters for operators and widths, and it just follows the original differentiable NAS works. And also, for the detailed form of this distillation loss, so we will use a content loss, a perceptual loss, and a TV loss, and their weighted sum to be our distillation loss. So the detailed training of parameters, we can just follow the SOTA works in GANs, and we do not need to hand tuning them. And also, we also decouple the computational loss into two parts. That is, for the computational aware loss, we will fix one architectural parameter and apply the penalty on the other one. So this is to avoid the architectural collapse phenomenon. So you can, so it's just like if we do not decouple the two parts of loss, the search generator may collapse to some operators with very heavy operators while very small widths. So this decouple is just to balance the width and operators. And finally, for the search algorithms, so we follow the standard differentiable NAS methods. So we will first pre-train the supernet and then do the search, and finally derive the final network based on the gamma and alpha mentioned before. And we also customize for our dedicated GAN applications. Since we will simultaneously search for the width and operators, so we will pre-train the supernet to make the evaluation of different operators more fair during the search process. So we will pre-train the supernet based on a sandwich rule proposed by previous work. So to pre-train the supernet, we will pre-train each operator with the largest width, the smallest width, and two random sampled widths. And also, to make our search process more memory efficient, we will apply a hard double softmax to sample the gamma instead of the soft weighted sum. So only one width is activated during our search process. So this is the main method of our AGD framework, and for more details, you may refer to the original paper. And finally, I will go to some evaluation results of our framework. So we mainly demo our AGD framework on two kinds of tasks, including the image-to-image translation and the super resolution. And our metric including the visualization results and also the quantitative results. So so first we can see some results of our framework on the unpaired image-to-image translation tasks. So for example, this task is house to zebra and zebra to house. So we list the visualization effect of a uncompressed SOTA cycle GAN on this task, and also a SOTA compression technique on cycle GAN, and our method. So you can see that compared with the SOTA uncompressed cycle GAN, we can achieve up to 11.2 times compression in floating point operations, and also up to 13.6 times compression in the model size. And you can see that we can achieve comparable visualization effect as the previous uncompressed cycle GANs. And compared with the SOTA compression techniques, we can achieve better textures. And also their method, you can see that they suffer from color shift, but we can better maintain the original color distribution. And also in terms of the quantitative results, we can compare with the SOTA compression techniques on GANs. We can still achieve up to, for example, 3 times reduction in model size and floating point operations with consistent quantitative result FID, and also notable better realization quality. And here's some evaluation on the super resolution task. So we compared our framework compressed on the ESR GAN, which is the SOTA method on the super resolution tasks. And you can see that we can achieve up to over 40 times compression in the model size, and with comparable visualization quality. So for more detailed compression, we also do a zooming here to see the visualization quality. So for the 3 methods, it's original uncompressed ESR GAN and a compressed ESR GAN by SOTA compression techniques and our method. So after zooming, you can see the local details. You can see that we can achieve maintain a better visualization quality compared with the previous SOTA compression techniques on GAN, and achieve more than 4 times compression in model size. And also in terms of the quantitative result, that is PSNR, we can surprisingly find that we can achieve comparable or better PSNR over the uncompressed SOTA ESR GAN. And also compared with the SOTA compression techniques, we can achieve about 4 times smaller model size. So finally, for a summary of our method, we propose the AGD framework, which is the first auto machine learning framework dedicated to GAN compression. And our method makes no assumption on the GAN structure, loss forms, or the availability of discriminators. And we can also outperform the existing options with aggressively compressed model size, floating point operations, and also real device latency without degrading the performance. So that's all for the presentation. So do you have any questions?
Thank you. I think we have time for maybe one question. I don't see any questions yet, but I'll ask one of my own. Can you explain the difference between distilling a model like this using sort of an auto distillation as you're proposing versus, say, just auto neural architecture search for a new model given the same task? Is there a difference?
In terms of techniques, there's no difference. So here we mainly use distillation to stabilize the searching process of GANs, because it's well known that the training process of GANs are very notorious, and also the searching process of a NAS method is also very unstable because you need to estimate the gradient. So we just use a distillation loss to stabilize the 2 processes if we want to combine them together. Yeah.
All right, thank you.
Okay, thank you.